Welcome back, everyone. This is Dr. Gallenstein here, and we are back again with an RStudio demo for lecture number 7. All right, let's jump right in. So as is usual, when we use R, we might need to use a package to have access to the programs or to the commands that we want. This time, if you haven't installed these already, go ahead and install these packages. I already have them, so I'm not going to install them. But go ahead and install the lmtest and the rcurl packages, because we'll use them today. All right, and we also need to tell R that we want to use certain packages, so that we use this library command, as we've used many times before, to tell R what packages we need to use. And then let's go ahead and import some data. We're going to use the wages for data set here. I'm just going to call it wages as is usual. All right, so there we go. We've got our wage data imported. So what we want to talk about today is heteroskedasticity. So lecture number 7 is on heteroskedasticity. Heteroskedasticity is where the error term for a regression model the variance of the error term for a regression model is dependent upon values of the independent variable. So it changes based on the value of an independent variable. What this does is it gives us biased estimates of the standard errors, and so we can't trust our hypothesis testing. So what we need to do when we run a regression is we need to kind of check to see, well, do we have heteroskedasticity? And if we do, how do we solve it? Okay, and so there's a couple of different ways to do this. There's some informal ways to check for heteroskedasticity, and then formal ways. So I'll just do a couple here, as we've already seen in Stata. So one way of checking for heteroskedasticity is just to plot, to produce a scatter plot of the dependent variable with respect to a handful of the independent variables. So let's just assume for the moment that we have, we have some model where we want to explain wages as some function of education and experience and maybe some other variables. Okay, so we just have this model in our mind, all right, and now we want to get some intuition, some informal intuition as to whether or not we might have heteroskedasticity. So let's just go ahead and produce some scatter plots using commands we've seen before. Let's produce some scatter plots for wage, the dependent variable, and the two independent variables that I've mentioned here. All right, so our scatter plot will come up here. And so what we're looking for is we're looking to see whether or not the variance of the dependent variable changes based on the value of independent variables. Okay, and the reason we're looking for that is because if the variance of the dependent variable changes based on values of the independent variables, then that is a good indication that the error term will also, that the variance of the error term will also vary by values of the independent variables. So that's why we're looking at this, and so here we go. We generated a scatter plot. And what we find is that the variance of the wage variable changes dramatically across values of education. We can see that at low levels of education, there's very few observations, and with it, very little variation. But then as we get up to high levels of education, there's a great deal of variance. So this right here is a great warning sign of heteroskedasticity. Let's check experience as well. Okay. Actually, we can see a very similar thing here too, where we see a lot of variance at low levels of experience and not very much variance at high levels of experience. So in both cases, we see some visual, some graphical evidence from a scatter plot that sends up a warning sign to us that we might have heteroskedasticity. Okay, so that's an informal way of doing it. Let's look at a formal way of doing it. And when I say formal, I mean some process that involves an actual statistical test. Okay, so the scatter plots don't involve a statistical test, but we're going to look at some that do involve a statistical test. So I'll do one by hand. This is the Bruch-Pagan test. I say it's by hand because I'm actually going to perform all of the steps in in R here. But then I'll also show you in a moment how to perform that same test just using an R command. Okay, so the Bruce-Pagan test, what we do is we run our regression model, and here we've got education and experience. We've also added female and married to our model. So here's our model: dependent variable, wage, independent variables, education, experience, female, married. Okay, so we can run our model. Let's just say that's the model that we want to estimate. And we want to know, is there heteroskedasticity in this model? Now, the reason we want to know that is because if there is heteroskedasticity, the variables that are heteroskedastic, we will not be able to trust the hypothesis testing. That means we can't trust this p-value and we can't trust the conclusions we draw from it. It means we don't really know if the variable or the variables are significant or not. So that's what we're looking for here. We're looking to see if we have heteroskedasticity so that we can know whether or not we can trust our p-values and know whether or not we need to solve for it. Okay, so we run our models, and now we want to perform the Bruce-Pagan test. Now, the steps for this is first we need to calculate the residuals. So we can calculate the residuals just by using this R command residuals and then putting in the name of the model. So model 1, we'll plug that into residuals. And we're going to save that value of the residuals as a variable in our wages data set. So that's what that line of code says. So we'll go ahead and run that. We can even see it. If we open up our data set, here is the residuals. Okay. All right, and then what we want to do is we want to plot. So we'll just do scatter plots, just to get an idea of it. So this is informal as well because we're just kind of getting a scatter plot feel, but we can use it to reinforce our intuition. Okay, we find again the residuals are very heteroskedastic. Now remember, heteroskedasticity is when the variance of the error term changes based on the value of an independent variable. The residual is kind of like an estimate of the errors. The residual is all the variation in the dependent variable that is not explained by the model. So the residual for each individual person, the residual is the dependent variable minus the predicted value of the model for that person. Okay, and so the residual is in a sense a kind of estimate of the error term, and so we can do our scatter plot, this time plotting residual versus education to see if the variance of the residual changes by the value of the independent variable. Again, kind of giving us an informal test. We see that it very much does. That reinforces our intuition. We see the same thing here for the experience. Okay, now continuing on with the Bruce-Pagan test, so what we do is we take that residual and we square it to create the squared residual. And then what we do is we rerun our model, except this time we use the squared residual as the dependent variable instead of wages. So basically what we're doing is we're taking the squared residual and regressing it on our model. Okay. And so what we're looking for here is we're looking to see whether or not our independent variables have explanatory power in this model. If they do, that gives us evidence for heteroskedasticity. And so we can see the F statistic is significant and the variables themselves are significant, which gives us an indication that there is heteroskedasticity. Okay, so now that's the Bruce-Pagan test in practice. Let's go ahead, or by hand I should say, let's go ahead and run the Bruce-Pagan test using the R command. So that is lm test BP for Bruce-Pagan test model 1. So just run that and it gives us an actual statistical output. We can see here it is the same p-value as the F statistic because that's what it's doing. So that p-value is clearly very tiny, so it is highly significant, which provides us evidence that there is heteroskedasticity. So just to be clear, the Bruce-Pagan test is testing the null hypothesis that there is no heteroskedasticity, aka that there's homoskedasticity. And so if we reject the null hypothesis, we conclude that there is heteroskedasticity. And so that's what we've just done. Okay, so now we feel pretty confident that we have heteroscedasticity in this model. So then how do we solve it? Well, for as complicated of a problem as heteroscedasticity is, the nice thing about it is that it's easy to solve. So what we'll do here is we just report what are called robust standard errors. That is, standard errors that are consistent or unbiased even in the presence of heteroscedasticity. So we'll report those. Now the way to do that in R is we use the summary command comma robust equals t, and when we use this robust equals t option, that tells Stata to report robust standard errors. But now, in order to use this summary command, so it's tricky, it has the same name, but it's a different command. We have to do this library r curl. We have to do library r curl, and then we can use the summary command that has this robust option. This robust equals t, that's robust equals true. That means it's going to report the robust standard errors. So let's do that. We'll report the robust standard errors for that same model, model 1. And so there we are. There we have it. We've diagnosed heteroscedasticity and we've solved it. So I hope you enjoyed the lecture, and I'll see you next time.